right, so we know that the sine is the opposite over the hypotenuse. And this ratio is the output of a sine function when you input theta. Okay, so there's an input-output. So the theta is the input, and the ratio, which is the opposite over the hypotenuse, is the output. Now that's true for acute angles, or when you actually are looking at a triangle, but generally speaking, the output is just a number. And for the sine, it's specifically a number between -1 and 1, because in any triangle, the hypotenuse is the largest side, and so the denominator will always be bigger than the top, or I guess equal to. And so in a fraction, when the bottom is the biggest number, the number is less than 1. Of course, sine can be negative, so it could be between -1 and 1. Okay, so we can then calculate things on the calculator. We talked about things like the sine of 30 degrees. Okay, this is one that we've seen the exact value for, but if we go to our calculator, you hit the sine button, and then the 30, put a parenthesis on there, and you get 0.5. Now we saw when we did our two special triangles that the sine of 30 is 1/2. Well, 1/2 and 0.5 are equal. Okay, and so we can use 0.5, or we could use 1/2 as a fraction. It doesn't really matter. But we also saw that, let's say, the cosine of 30 degrees, that was, according to our special triangles, what was the cosine of 30? It was square root of 2 over 2, I believe, right? So that should be square root of 2 over 2. Let's just double check that. So if I go to cosine of 30 on the calculator, it's going to give me a decimal, 0.866 roughly, right? Well, if I were to calculate square root of 2 on the calculator, oh, I don't get that. That's because it should be square root of 3 over 2. Nope. Right, there it is. So that should have been a square root of 3. My mistake. Square root of 3 over 2, which is approximately 0.866. Okay, so you can kind of see that's actually a nice little check. So if I'm trying to go off of memory, it's kind of nice that worked out poorly, interestingly enough. If I'm trying to do a quick check on that, trying to go off of memory, I can always check myself with the calculator. Okay, so anyway, so the input there is 30 degrees. The output is the ratio of root 3 over 2, or 0.866 approximately. Okay. Now, our preference, generally speaking, is to use exact values when they're available. But a lot of these, we won't really know the exact value, or won't be able to calculate them very easily. And so the decimal expansion, rounded somewhere, depending on the problem, is going to be sufficient. Okay, so our calculators have a sine, a cosine, and a tangent button. They do not have a cosecant, secant, and cotangent button. And so if I wanted to calculate something like the cotangent of, let's say, 60 degrees, the cotangent of 60 degrees is actually equal to 1 over the tangent of 60 degrees. You guys will recall that the cotangent and the tangent are reciprocals of each other. And so if I calculate 1 divided by the tangent of 60, that will give me the cotangent of 60, which is approximately 0.577. I'm going to round these to 3 places after the decimal, the nearest thousandth. Okay. And then let's see, the tangent And that should be, is that 1 over root 3? Just to check here. Yes, sir. Okay, 1 over root 3 it is. So the tangent of 60 is the square root of 3, so cotangent would be 1 over the square root of 3, and that does work out to 0.577. Okay, so that is just a quick idea. So your input is an angle here. Input is angle, and the output is a ratio. Okay, it's either the opposite over adjacent or adjacent over hypotenuse or something, right? So it's some sort of ratio, but essentially it's just a number going in and a number coming out. Okay, now when you have a function, you can also think of these as a one-to-one function. There's some theory behind this, but you have to do you have to do a little limiting of the domain, which we'll talk about actually. I think in chapter 6 we get into these a little bit more, but we're going to talk about something called the inverse trig functions. And with inverse trig functions, you essentially inverse or invert the outputs and inputs. And so with an inverse trig function, the input is the ratio, whereas the output is the angle. Okay, so an inverse trig function, I might say, if I wanted to do sine, for instance, I might do the inverse sine. And the inverse, we use a little -1 superscript. It's a superscript like an exponent, but it's not really an exponent. With the trig functions, it's a notation that represents an inverse. So I might say the inverse sine of 0.5 is equal to 30 degrees. And so what happens then is with the sine, the input is an angle and the output is the ratio. With the inverse sine, the input is the ratio and the output is the angle. I can show that on the calculator as well. The sine, cosine, tangent buttons have inverse trig functions on them. And so if I want the inverse sine, I hit second and then sine. If I type in 0.5, I'll get a 30-degree answer. And remember, the calculator is in degree mode, and so these outputs will be in degree units. In a similar way, if I did the cotangent, I could do an inverse cotangent of 0.577. And in theory, I should get, now this will be an approximate because I've rounded this value off, I should get approximately 60 degrees. The problem is, I don't actually have a cotangent button on here, nor do I have an inverse cotangent. And so I can't immediately get that answer. So the question is, how would I get that? If I didn't already know this line, if I was doing this from scratch and I wanted to calculate the left side, how would I get that 60-degree answer? And it's a little bit complicated, and so follow me on this. Basically, the idea is, let's see, so we know that the tangent and the cotangent are reciprocals, right? And so the tangent of theta is opposite over adjacent. And so the inverse tangent, I might have to slide this up a smidge. The inverse tangent of theta, oh no, I did that wrong. I'll write over here. The inverse tangent of the opposite over the adjacent is equal to theta. Okay, so in one, you input the angle, you get out the ratio, and the other you input the ratio and get out the angle. Okay, so now I know that the cotangent is the reciprocal, adjacent over opposite. And so when I do the inverse cotangent, it'd be the inverse cotangent of the adjacent over the opposite. Okay? So, if I'm trying to find the inverse cotangent of a ratio, it's the same, this theta, well, the inverse cotangent of a ratio is the same as the inverse tangent of its reciprocal, if that makes sense. And so I should be able to calculate, so the cotangent of, the inverse cotangent of 0.577 should be equal to the inverse tangent of 1 over 0.577. Okay. Oops, I should slide that up. So the inverse cotangent of 0.577 is equal to the inverse tangent of 1 over 0.577. Let's double check that on the calculator to make sure it works. If I were to type in the inverse tangent of 1 divided by 0.577, that gives me very close to 60 degrees, right? It's off a smidge. We'll say approximately 60 degrees. It's off a little bit, and that little bit that it's off is due to the rounding that we did with that initial 0.577. Okay. All right, so the inverse trig functions are a little bit messy when you're dealing with the cotangent, the cosecant, and the secant. You have to do a reciprocal of the input and then put it into the other trig function. Okay, it's cofunction, or it's reciprocal function. Let me give you a couple more examples. Let's try something like the inverse secant of 1.87. Okay, inverse secant of 1.87. Well, remember, the 1.87 is the input, but it's a ratio. The output is going to be an angle. So we'll call this theta. Okay, and if you think about it, inverse secant, well, secant is the reciprocal of the cosine. And so if I want to calculate this, I'm going to use the inverse cosine, but I have to do the reciprocal of the of the ratio. And that should equal the angle theta. Okay? And so if I calculate that, I'm going to want an approximate here. So the inverse cosine of 1 over 1.87 is approximately a 57.7 degree angle. Okay, so remember, the inverse trig functions give you angles as outputs. The ratios will be the inputs. The other thing we have to deal with when we work with approximations like this are going to be dealing with negative numbers for the angle. Okay, so if you had, or some other, maybe not even negative numbers, but angles that are not acute angles. So angles that are in the second, third, or fourth quadrants. It doesn't look like you're going to see many of these. Actually, it doesn't look like you're going to see any of these in this section, and so I may actually ignore. Oh, there's a few of them. There is. Okay. So something like the inverse cosecant of negative let's go 4.5. Okay. Well, again, the negative 4.5 is a ratio, and the cosecant is the inverse of the sine. So we look at the inverse sine of 1 over negative 4.5. And that should give us a good answer. This isn't quite the example I was looking for. Negative 1 over negative 4.5 is approximately negative 12.84 degrees. Well, that degree measure is not one that we deal with a whole lot. What is interesting is that these inverse trig functions give us values, but they only give you one output. There are often, pretty much every time, there are going to be two angles between 0 and 360 that give us that actually give us those trig functions. And so, for instance, 57.7 is not the only angle that has a secant value of 1.87. And negative 12.84 is not the only angle that has a cosecant value of negative 4.5. So what we would like to do is find all the other angles. Okay. If I go back to this previous example, 57.7 is in the first quadrant, which makes sense because the secant is positive, the cosine is positive in the first quadrant. But remember that ASTC, the cosine is also positive in the fourth quadrant. So is there a fourth quadrant angle where this is the reference angle? And the answer is yes. It is, of course, 360 minus 57.7. And that should give you, what's that, 302.3? I believe. If I did that, let's double check it. 360 minus 57.7, 302.3. Yep, there it is. Okay, so there's actually two angles that give us a secant value of 1.87. Your calculator is only going to give you one of those angles. In this other example here, the later one, negative 12.84 is not in the interval from 0 to 360, but generally we want our angles to be in that interval. And so I might convert that. Now, negative 12 degree angle, if you add 360, you're going to get a fourth quadrant angle. So I might take negative 12.84, add 360, and that will give me a 347.16 degree angle. That's a fourth quadrant angle. Remember, the sine is negative. This is a negative value in both the fourth and third quadrants. So how do I find another angle similar to this but in the third quadrant? Well, if you come 12 degrees down, or 12.8 degrees down, my handwriting's getting bad, into the fourth quadrant, that's equivalent to the same angle coming down in the third quadrant. Well, to find that angle, you take 180 degrees and then add the 12.84. I can't even speak it. So you would take 180 plus 12.84, and that would give you what, 200, no, I had it right the first time, 192.84. That's the other angle. So there's actually two angles between 0 and 360 whose inverse sine, or whose inverse cosecant is, or that has the inverse cosecant of negative 4.5. Okay, so hopefully that helps out with this section. The calculator can be a bit tricky because of the fact that you don't have a cosecant, secant, or cotangent button, and therefore you don't get the inverses of those. But hopefully you can see how when you calculate the inverse of one of those three functions, you have to use the reciprocal function and calculate the reciprocal of the input before you get the output. It is a bit confusing, but work through several examples and hopefully you'll get the hang of it.